Hi everyone, today we want to do just a little bit of vector math, and it's mostly review from what we've done before. And to start off that review, let's talk about what a vector is. It's really just a special type of number that has not just a size, but it also has a direction. Most of the regular numbers we're used to are called scalars, and they have just a size. And the example of that would be like 3 meters or 127 flamin' hot Cheetos. Whereas a vector has a little bit more information. You could say 3 meters north, or 42 meters per second at 128 degrees. The size of a vector we call the magnitude. We notate a vector with a little arrow symbol above the letter, so we have vector v, and to denote the magnitude, if we just want the size of it, we note it with same thing with double absolute value signs around it, just to denote the magnitude of the vector. There is a way to denote just the direction of a vector, and we'll get there next week. So, there are essentially two ways to talk about vectors. You can note them by magnitude and direction, or by just their components. Magnitude and direction is pretty self-explanatory. You could have a vector like we said above. I think it was 42 meters per second at, what was it, 128 degrees. We take that 128 degrees usually from the plus x direction, so it's the x-axis going in the positive direction, and we measure counterclockwise from that axis. So 128 degrees would be, well, there's 90. 128 would be somewhere in here. So our vector would look like this. 42 meters per second, which is the velocity, and this angle would be 128 degrees. Doing it by components is actually a little bit more difficult. Or I suppose a little bit more counterintuitive. We would say something like, we would take this kind of vector and break it up into two smaller guys, one going purely in the y direction, so up and down. In this case, it goes up. And a different one going purely in the x direction, going back and forth. In this case, it goes off to the left, which would be a negative x vector in this particular case. These two, the x and y components, add back up to the original. Remember, when you're adding vectors, you start at the very tail of the first one, you follow it like you're walking it as a path, then you walk the second one, and the result vector goes from the tail of your first to the tip of the second. And in fact, you can add quite a lot more than two, any number of vectors you want, as long as you start where the first vector started and end where the second one or the last one stops. That's adding all your vectors up graphically. Okay, so we could write this a few ways. Say, for example, not this particular vector, we could write it as a different vector as, I don't know, 1x plus 4y. This would be the component form. Or you could write it a little bit even more compactly as an ordered pair, 1, 4, which is just the end point of the vector. This is kind of assuming that you're starting your vector at 0, 0, at the origin, whereas this one, you can start it anywhere you want. Okay, so let's look here. The biggest thing we need to do is to convert between these two forms of vectors. And just remember, these two are not the same vector, they're just two different examples. To do that, we need sine, cosine, and tangent, our trig functions. Let's really quickly define what those are. Sine is, in terms of right triangles, a function. So it's some mathematical thing that you stick a number into and it gives you another number out. And I'm going to call this the hypotenuse over here of the triangle. Since we have x and y as our lengths and the hypotenuse here, sine is defined, sine of this angle theta, I should say, that letter is a Greek theta. Sine of that angle is defined thusly. Sine of theta is the opposite side from theta. So in this case, you take the angle and you go to whichever side it's not touching. In this case, it's y. So the length of y, it might be the magnitude even if it's a vector, divided by the length of the hypotenuse. Cosine of theta is pretty similar, only it's the adjacent leg of the triangle. In this case, the one that's touching it that's not the hypotenuse. In this case, it's x divided by the length of the hypotenuse. And finally, tangent is y over x. In this case, it's y over x. More generally, it's just the opposite leg, whichever leg is not touching your angle you're interested in, divided by the leg that is not the hypotenuse that is touching it. So I'm going to write these little mnemonics here. There's opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. Hopefully you've heard the way to remember these three really simply, SOHCAHTOA. So this just stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. That'll save your butt a lot of times. Okay, so then let's do two really quick examples of how to convert between these two forms of vectors. Let's take the first vector as, let's say it's 15 meters long at, I don't know, 224 degrees. If we draw that out, and I'm going to suggest you always draw out physics problems when you're starting them because it really helps to visualize. 224 degrees, well, let's see, where's that going to be? 90 is here to the y-axis, 180 is all the way back to the negative x-axis, and 270 is all the way down here to the negative y-axis. So it's somewhere in this third quadrant, and I guess we can number the quadrants. 1, 2, 3, 4, like that. So yeah, it's somewhere down here. Something like that. There's our vector. And there's our big angle. What we want to do is we want to make this into a nice triangle with x and y components. I want you to note that both of these x and y components in this triangle are negative. That's because the x is going here in the opposite direction of the positive x-axis, and y is going down here, opposite to the positive y-axis. Okay, so at the end of this problem, we're going to need to remember to put a negative into both of our x's and y's, because it might not come out of the math. Let's just make sure, a mental note just to check. In order to do this math, though, we need to figure out what this little interior angle in the triangle is. We know the big one is 224, and we know all the way to here is 180. So if we do 224, the entire big one, minus 180, we should get just this left over. 224 degrees minus 180 degrees is going to be, what is that, 44 degrees? Yes, 44 degrees, which is pretty close to 45, so I actually drew it pretty darn close to what it ought to look like. I'm going to draw this triangle just a little bigger over here with a hypotenuse of 15, and we're going to draw in x and y legs for it here. Here's y, and I'll label it, I should say. There's y, and here's x. And between x and the hypotenuse, that's 15, we know now that we have a 44 degree angle. In order to get y and x, we're going to use some of our trig functions. I'm going to use the basic ones. I'm going to use sine first. Sine of 44 degrees is going to be the opposite leg from the angle divided by the length of the hypotenuse, which is 15. In this case, the opposite leg is y. It's opposite the 44. So I'm going to put my y, which is the answer I want to get eventually, divided by 15. If I do some algebra to this, I'm going to get 15 times sine 44 degrees equals y. And if I plug this into a calculator really quickly, I get that y is 10.42, let's say meters, because our original unit was meters, so we're going to keep that. Now we want to remind ourselves at the end here that it's negative 10.42 because it's going down from the origin, or from the x-axis there. So it's a negative 10.42 meters. Very similar calculation for x. Cosine of 44 degrees is going to be equal to x, as soon as I switch colors here, x divided by the same 15, that hypotenuse again, because x is the adjacent leg to our angle, and pretty close to the same calculation. So we plug this into our calculator. It should be pretty close to 10.42, since it is indeed almost a 45-degree angle. If it was 45, it would be exactly the same as the y component. I get 10.79 meters. And of course, I'm rounding on both of these to just 2 decimal places. Again, we need to remind ourselves this is a negative 10.79 meters because this x is going in the negative x direction. So if we want to write this finally in one of our, say our component form, we could say that vector, I never gave it a name, let's call it vector A, because it's the first one. Vector A is, let's say, negative 10.79 x minus, there's your negative, 10.42 y. And that is the component form of that vector. To go the other direction, it's a little bit more complicated, but not honestly that bad. Let's take the vector, vector B, I'll call it, 5x, and we'll do minus 7y. An easy way to get the hypotenuse of this vector, and you know what, I'm going to draw it out first using the same colors. Blue for x, it's going to be length of 5, and red for y, it's going to be a length of negative 7, so it's going down. And the hypotenuse is going to go from the start of x to the end of y here. We want to get this length, question mark is what I'll call it for now. You can probably guess the easiest way to get this length is the Pythagorean theorem. In fact, rather than question mark, I'll call it C. Pythagorean theorem, of course, is a squared plus b squared equals c squared. So that c is the square root of a squared plus b squared. There should be a plus or minus here if we're being really honest with the math, but since this is the length of our hypotenuse and we're going into this certain magnitude at angle format, we don't care about the negative, we just care about the positive. If I plug 5 squared plus negative 7 squared into my calculator and take a square root of them, I get a hypotenuse of 8, ooh, that's a funky 8.602, let's say meters. It's a nice standard unit for us. There's our hypotenuse, we'll have to remember that. And secondly, we want to look for an angle. Since this is the positive x-axis here, I'm going to look for this angle in the triangle here. Remember, we do want to get all the way around going counterclockwise. So at the end, if we have this angle, we're going to want to figure out the bigger angle, and we'll deal with that right at the end. There's a couple ways to do this. I think the easiest way, I'm going to use the inverse tangent. So I'm hoping everyone has heard about functions. If not, here's a very quick reminder. Function is sort of like a little machine. You put number into it, in this case x, and it spits out some other number, maybe y. It's like clockwork, and it works via various machinery. There is a way to calculate what sine, cosine, tangent, and all the trig functions actually do without using a calculator. It's a little complicated. It's not something we need to get into. The example I like to use here of functions is f of x is x squared. So the function is squaring, basically, and x is the number that you put into the function. It's like you've got a toaster that toasts bread. The x is the toast. The function is the toaster that's doing the stuff to it. So I can plug in, 4 into x, and what it spits out is 4 squared. I should not have written 4 equals 4 squared. That's not true. But you know what I mean. 4 squared is 16. So that's what functions do to numbers when you spit them in. If I want to undo a function, I can use the inverse. I think the notation for that is a little hash mark, a little prime. So if I take the inverse, if I plug 16 into the inverse of squaring, I get 4 back out. And actually the inverse of squaring is square rooting. Right? So in that exact same way, sine, cosine, and tangent and all the trig functions have inverse functions. The way we write them is to a little -1. It doesn't mean to the power of -1. It means inverse in this particular case. It gets confusing, I know. There's actually an alternate way to write all 3 of these. You could also write arc sine, arc tangent, or arc cosine first, and arc tan. And a really quick way to write all these is a sine, a cos, and a tan. If you don't want to get mixed up with the negative ones, any of these is totally fine. I am okay with any of these 3. So what I'm going to do in order to get our angle is use an arctangent. So let's first look at this. A tangent of our mystery angle, and I'm going to name it theta because it's my favorite letter for angles. The definition of tangent tells us that tangent of theta is going to be the opposite leg, the opposite length, which is -7 in this case, divided by the adjacent length, which is 5. So I'm going to say -7 over 5 is our tangent theta. In order to figure this out, we need to undo tangent of theta, and we need to undo it on the -7/5 here. We're inversing this function. So what we're doing is tan, inverse tan of tan. In this case, let me finish writing this out for you. In this case, on the left-hand side, inverse tan of tangent is just going to give theta. If you're undoing the tangent, and that's all that's going on, you just get that. And then, let me not forget the -1 there. This inverse tangent is a function in your calculator. It's right above the tangent button itself. You'll need to use the little, in my calculator, it's a little blue second function button. So the inverse tangent is written in little text right above the button that says tangent, not its own button. Okay, and when I plug that in, I get theta, our angle. Let's see. If I plug it in, I get theta is -54.46 degrees. And remember, this is kind of important. The negative here is interesting. So we've defined angles as starting at the positive x-axis and then going around counterclockwise in this direction. A negative here means that it's going in the opposite direction. So now it's actually going from the positive x-axis clockwise around like this. So that's just measuring this angle downwards. So in order to get what the whole big angle, the standard counterclockwise angle is, I'm going to take this negative 54.46 and add it to 360. Basically, I'm taking 360 minus 54.46 to get my final answer. That's going to be this leftover, because the whole way around is 360, and you subtract off the 54.46. So I get my angle, I'm just going to draw a little angle symbol, finally is 305.54 degrees. So if I want to write down an answer here, I'm going to have to say this vector is 8.602 meters. Remember, we had that from over here. That's the length. And it's at 305.54 degrees. And we've converted it. All right. That's about it, you guys. It can be a little complicated, and it can be confusing to see at first, but I hope that you're feeling okay about it, and we will see a lot more of this kind of stuff, and we'll do a lot more practice in the weeks to come. Thanks, everybody. Have a great day.